Welcome. We now begin chapter 6, and the topic is the normal distribution. So we've seen normal distributions previously. These were our bell curves, but in this chapter, we're going to be able to go into more depth, in particular, because we will make use of our graphing calculators. So it says here that the Gaussian distribution, so Gaussian distribution, just another name for a normal distribution, which we do often refer to as a bell curve. It is a continuous probability distribution. So unlike the last chapter, which was on discrete probability distributions, now as we switch over to random variables that are continuous, it means that our values for X can take on any value, infinitely many possibilities. So I just came over here and labeled my x-axis, my random variable. And here where it says domain, that X has a domain from -infinity to infinity, it means that in theory, these graphs go forever to the right and forever to the left. But what we want to keep in mind, practically speaking, is that on a bell curve, most of the data will be towards the center, which is established by the mean. So most data, most of the area is here. As we move further from the mean to the left and to the right, you'll see this area getting smaller and smaller and smaller. So less of a chance of values that are far from the mean. So I am going to make a note up here that as we talk about shading graphs, if we took a look at the whole bell, the area under that curve, so the area under the curve would be 100%. So we'll start talking about regions under the graph, but if I look at that curve and I shaded the whole thing, it would represent 100% of that picture. So we'll come back to a reference to that in a bit. Now let me come back to this function f of x. So the function whose graph is a bell curve may look a little bit overwhelming. Fortunately, we're not going to have to deal with it directly, but I did want to show you the function and point out some familiar symbols. So I see a mu for population mean. I see a sigma, population standard deviation. And those two values are called the parameters of the normal distribution, and they'll determine what our bell curve actually looks like. So it says normal distributions are a family of distributions because there's not just one normal distribution, there are actually infinitely many, but each one is determined by its mean and its standard deviation. All right, so the mean, mu, determines the center. The standard deviation sigma determines the spread of the distribution away from the mean. And all normal distributions are symmetric about their mean. All right, so we'll recap all of that by looking at a specific example. So it says that Chester's churros have calorie amounts that follow a normal distribution with mean 300 and standard deviation 30. We'll let our random variable x be the calories in a Chester's churro. All right, so the population parameters that describe that normal distribution would be the mean, and the symbol for population mean is mu. So that is 300. And that tells us the center of the distribution, so that's 300. So if you went out and bought a churro, X would be the calories in your churro, and most of the time I expect it to have around 300 calories, with extremes away from the mean being more and more unlikely. All right, so population standard deviation is 30, and we're going to review what that tells us from a previous chapter. We learned the empirical rule for bell-shaped data. So what we're about to do here may hopefully look a bit familiar. So if the mean is 300, And sigma, standard deviation, is 30. I'm just going to put 30 on the picture there. We learned previously that if we stay within 1 standard deviation of the mean, so if we went 1 standard deviation above the mean, so 300 plus another 30 would be 330, and 1 standard deviation below the mean, 300 minus 30, 270. So previously we learned, just going to come up here to the top. Previously we learned that that would be about 68% of our data. So we basically just memorized that number before, and we said that the empirical rule tells us that about 68% of data is within 1 standard deviation of the mean. And what I'm going to do now, just for emphasis in terms of shading, so if I were to shade that region between 270 and 330, that's clearly not 100% of the picture. It's about 68% of that picture. Okay, we did learn some additional percentages that went with our bell curve. So we had started at the mean, we had added a standard deviation, and we'd actually done that 2 more times. So we added another standard deviation. So that would get us to 360, and then another standard deviation, 390 on the other end, just subtracting 30. So previously in the course, I could only ask questions that involved one of those numbers I've now written down. But now with the help of technology, you'll be able to work with any number on the x-axis. So for example, a churro between 340 calories and 370.8 calories. So any values will now be open to us as we move forward. All right, the other thing that will be nice about technology is we'll be able to get a little bit more accuracy in our answers rather than just saying a whole percent, 68. So let's see how this works with our calculator. So let me get my calculator up for you. Okay, so now it says, find the probability that a randomly selected churro has between 270 and 330 calories. And we'll write that here symbolically. So probability that X is between those values. All right, so we know the answer is about 68%, but let's take a look at how technology can help us here. So we're going to have a distribution on our calculator, normal. And we're going to use normal CDF to find the area between 2 values that define that area. So the way it works is we're going to specify an area by establishing a lower bound and an upper bound. I'll point that out on the graph in a second. And we'll also need to tell the calculator the mean and the standard deviation of our particular normal distribution. Okay, so up here on my picture then, this region is defined by 270, that would be its lower bound, and 330 would be its upper bound. So we're interested in this area between those values, or that probability. All right, then we're ready to substitute. So we're just going to shorthand normal CDF. We'll just write NCDF, and then we'll go from 270 to 330 calories. And then the mean in this instance is 300 and standard deviation is 30. Okay, so back to our distributions as we've done previously. And this time normal CDF and 270, comma 330, and 300 for mu and 30 for sigma. And enter. All right, we're going to round that to 4 decimal places. So that's 0.6827. And we'll often be staying in decimal, but let's talk percent here. So that would be 68.27%. So again, we're just being a little bit more precise. So rather than saying about a 68% chance, now we can say about 68.27%. So we're still rounding, but we just improved our accuracy a bit. Okay, next step. So we also previously in the course talked about z-scores. So on this number line below, I'm going to now label that z. And what we're going to do is transform this distribution into a new normal distribution called the standard normal distribution. So I will talk more about that in a second. Let's just first do a little bit of converting. So let's say that we had a churro with 300 calories and I wanted to know its z-score. So our z-score formula was z equals x minus mu over sigma. Okay, so if you bought a churro with 300 calories and you found out how different that was from an average churro, well, the average churro was 300 calories, and you wanted to know how many standard deviations that was, that's why we divide by sigma. So, of course, in the numerator, you're going to get 0, and 0 divided by 30 is 0. So up on my graph here, whatever the mean is for your normal distribution, when we convert it to a z-score, if you get a value that's equal to the mean, that will always give you a z-score of 0. All right, let's do one other value. So what would be the z-score if a churro had 330 calories? So again, z is x minus mu over sigma. So a 330 calorie churro, to see how different it is from the average churro in terms of how many standard deviations that is. All right, so now my numerator is 30, so that churro is 30 calories above average. And how many standard deviations above average is it? So 30 divided by 30 is 1. So up here on my z-axis, if you get a value 1 standard deviation above average, its z-score will always be 1. Okay, so I won't convert all of them, but we'll just point out here that if we were to get a churro with 270 calories, it would be 1 standard deviation below average. So now you would have a -1 to indicate it is below average by 1 standard deviation. And then again, just filling in our remaining values. So z-scores don't have units to them. They're simply an indication of a real number on the number line. And z-scores don't have to be whole numbers. So for example, you could have a churro between 330 and 360, like 340 calories. Its z-score would be somewhere between 1 and 2. So we're going to see all sorts of different z-scores coming up. All right, so if I were to graph a new graph here with the z-axis, this distribution would be called standard normal. So it's a very special case of a bell curve. What makes it special is that its mean, mu, so the center of that distribution is 0, and the standard deviation, this distance then, is not going to be 30 anymore. That would be just a distance of 1. So that graph, if we were to graph a standard normal distribution, would have those parameters. All right, so this means that when we're working with our calculator normal CDF, we can work with the original distribution, or we can work with the standard normal distribution. So now this question, what is the probability a randomly selected z-score is between -1 and 1? So that answer should be the same as the last answer. because we're still defining an equivalent area. It's just on a different scale here. So our standard normal. All right, so here is what we'll do then. So let's go from, instead of x, z, so -1 to 1. So it's still going to be normal CDF. But now our lower bound will be -1. Our upper bound will be 1. The mean will be 0, and the standard deviation will be 1. Okay, so it turns out that the mu 0 and sigma 1 is the default on our graphing calculators. So what this means is that we'll be able to do a little bit of shorting the data entry here. So I don't know if you hear Chester barking back there, but I'm going to keep this video going. He's being quite loud. All right, so normal CDF, if we just say the lower bound and the upper bound, but we leave off a mu and a sigma. So if you leave off the mu and the sigma, the graphing calculator will assume you mean this. So we say that standard normal is the default on our calculators. So if it's a regular normal distribution, we have to give the calculator the mean and the standard deviation. If it's standard normal, we can leave those values out and the calculator just assumes that's what we are talking about. All right, so that's what default means. All right, so let's do it. So normal CDF. All right, so we need to enter -1. So remember to enter a negative. You're going to hit your negation button. So don't use your subtraction button, negate. So -1, comma 1. And you might have noticed again, I don't generally close parentheses, so you can if you would like, but we don't need to. And again, same answer. So it's an equivalent area as the last one. So 0.6827 or 68.27%. Okay, so we're going to need to deal with standard normal a lot. So as we move forward, we're going to spend this first section just working with standard normal, and then we'll switch back to random variable X as we do applications once we are done with our standard normal work. And just moving forward here, anytime that we use the variable Z, we're going to assume that that variable follows the standard normal distribution. Okay, and we'll move forward from here.